basically the idea of having a flying humanoid robot, which is actually the guy on my right hand side here. My background was on flight dynamics and aerodynamics. Was 2020 when the robot started balancing very well, when the robot started walking very well. We thought, no, now this is the time probably to start working on flying. Back at the time, the idea was really similar to that of Iron Man. We said, why don't we try to basically have a humanoid robot with jets? Very soon we discovered that the Iron Man idea was wrong. It was wrong because
So if you're enjoying this podcast or even just the idea of what you are building, please hit the subscribe button. It might seem small, but it's a little way of saying thank you. You believe in what you're doing. We are building the biggest tech-related community podcast in Africa, brick by brick, voice by voice. So subscribing is like a tiny little donation, but with massive impact. So if this matters to you, support it for a long run. Thank you. Good day, Professor Daniele. It's a very good pleasure to have you. And we know you as the designer to the world's first flying humanoid robots, and we'd like to discuss on the topic what you guys are doing, what you guys are building. So we know what they call Cub3. So what was the original version, mission and vision behind taking the Cube humanoid platform and turning it into a jet-powered flyer robot?
So basically the idea of having a flying humanoid robot, which is actually the guy on my right hand side here, came sincerely speaking when I arrived at IIT. We are basically talking about 2013 because my background was on flight dynamics and aerodynamics. I did my PhD in France and I'll be working on aerial vehicles. So when I came to IIT and I saw this platform, iCub more precisely, I thought, why don't we try to make it fly? Clearly, this idea then took a long time because back at that time, iCub didn't even walk, didn't even balance. So more or less for the first 6-7 years, we've been focusing on other aspects rather than flying. And then we thought probably it was 2020 when the robot started balancing very well, when the robot started walking very well. We thought, no, now this is the time probably to start working on flying. And the idea that we had a few years before started being implemented.
Okay, so how did the artificial and mechanical intelligence AMI lab at IIT decided that infantry scale humanoid flight was feasible?
Yes, so this was not very easy, I have to say. So just to tell you that the first paper, so the first piece of equation that we wrote about what we call aerial humanoid robotics, which is this new field of engineering that we're trying to conceive, was laid down in 2017. So the first equation that was meant to analyze whether or not a flying humanoid robot was feasible now is basically 8 years. So starting from that equation, starting from those equations, back at the time, the idea was really similar to that of Iron Man. We said, why don't we try to basically have a humanoid robot with jets attached to the hands and also attached to the feet? So very soon we discovered that the Iron Man idea was wrong. It was wrong because let me make you this example. So if you have if you want to make a balance this, and if you keep it with your hand below, basically this is inherently unstable. So if you have thrust forces at your feet, the system is going to be inherently unstable. Instead, if you pick it up above the center of mass, then the system becomes stable. So that's why we thought, no, come on. After a couple of years analysis, we understood that it was not really smart to put a jet at the feet, but then we had to understand how to place and if then it was possible to place jets in a jetpack. So the feasibility journey is very long. And I remember this moment, which was which is a funny one. So we basically submitted this paper, the first paper ever on flying humanoid robot, into the robotics conferences, where basically how does it work? You have an idea, you write a paper, and then you submit the paper, and someone else reviews the paper and tells you this is a good idea or this is a bad idea. So when the paper went back, they said, okay, mathematically it's good, but what about the engineering feasibility of this? So in the time from the moment that we received the feedback and we had to submit the rebuttal, there was a guy called Richard Browning from Gravity that basically had the idea of trying jets attached to his body. And now, I mean, Richard is a friend of mine. So back at that time, clearly we didn't know each other. There was this video of this crazy guy installing jets on his body, and we just sent the link to the video to the reviewer saying, if a man can do it, a humanoid robot will. And that's somehow the one of the answers that we gave back in time, that we were not sure because nobody did it. But anyways, we tried iteration after iteration, and since Richard Browning was able to do it, then probably a human might also have achieved in the same task.
So you said it took you guys have gone through iteration. So how long has this iteration been? How long has it been?
So we had more or less three big iterations, Joshua, because they were the three iterations that led us to iRon Cub3. So we had the first iteration where we were not really able to understand to have jets on a platform that was not even the robot, but we called it Iron Cup. But then we saw everything on the Iron Cup 2, that is not basically here, it's in the other side of the lab, and now it's a piece of history. And then we landed on Iron Cup 3, which is our latest iterations. So we have the robot is basically, it has some sensors, like 4 sensors, and also new control algorithms that are based on AI in order to basically take off the land.
So what past prototypes are your Iron Cube MK want to pave the way to the current Iron Cube 3, and what lessons were learned? So what past prototype paved the way to the current one you have, and what lessons were learned?
Yeah, so basically we learned 3 big things from the early days to the Iron Cup 3. So the first one was that making experiments with these beasts is very complex. So you have to know that there is a supersonic gas getting out of the nozzles and noisy, and also temperatures around 800 degrees Celsius. So the complexity around the experimental area is not easy to deal with. So that's the first big issue. So you have to have a proper experimental area, and you have to also learn. So it's not only a problem of making the robots fly, or because there might be some robotics say, hey, but these are 4 forces, you attach to something, you make it fly with, I don't know, QP, which is one of the things that robotics do. No, that's not like that. So the complexity is also around the robot itself. Then the second thing that we learned is that aerodynamics and thermodynamics play a pivotal role. So you have to really work on these 2 topics and understand how to integrate aerodynamics and thermodynamics inside your control algorithms, especially for modeling the jets, disturbance rejections, and these kind of basically properties that the robot has to have while achieving flight. And the third one is that the control algorithms for a fly humanoid robot equipped with jet engines are inherently different than those of a humanoid robot or a quadrotor. Because, one of the biggest challenges come from the fact that the bandwidth, so the response time of the jets is very, very different with respect to the bandwidth of the motors, of the electrical motors of the robot. So the robot can move his arms very quickly, but can change the thrust not as quick. So basically, the control algorithms have to be designed in a way that this problem is taken into account.
Okay, so what were the biggest engineering hurdle to integrating the 4-jet engines into the 7 kilogram humanoid frame? Yeah.
So the biggest issues really came also from understanding whether or not the robot was about to break. So we had to add the least amount of weight while retaining the safety of the robot. So I've been working on that extensively in order to ensure that the robot was not breaking apart. And actually, this happened a couple of times. So we had to be sure that the robot was not exploding.
Okay. So how did the design of the titanium spine and the heat-resistant panel evolve to handle 80-degree exhaust?
Yeah, so one of the things that actually we did in order to design the Aeron Cub3 was to combine the AI with the physics of the robot. So that's something that we are really proud of, and we think that the next generation of physical AI will be based on these techniques. So we were able to basically have AI algorithms that take into account the physics and then generate optimal designs and also optimal policies controlling the robot. So the idea was basically that one: get AI and mix it with physics so that the robot didn't have to be designed by a man or a woman or an engineer in general, but these were the output of an AI. So the design of the robot had to be the output.
Okay, so I think that is the titanium, right, you are talking about. How did you test such dangerous robots' safety in early flight experiments? Yeah.
Yeah, at a certain point, I have to say that we have to release the bloopers of this. Actually, yeah, that was not easy. There is really little room for improvisation, and you have to iteratively understand what is going wrong, what is not going good. So you have full pressure, you have temperature of the exhaustion gas, you have the control algorithms, you have safety thresholds not to exceed. So there is not a single answer, but it's an iterative process that you turn the jet engines on, and then you see what happens, and then you keep iterating.
Okay, so now there's one exciting question I would like to know about this Cub3, right? So what mechanical and aerodynamic stimulation tools were critical in the design validation? I think that is a very interesting question to ask here.
Yeah, so basically simulations are the so-called digital twin of the robot. So simulations are important because you have to understand whether or not the robot is going to do crazy stuff and behave weirdly with respect to what you expect. But there is always this what is called the sim to real gap. So in robotics, this is a big problem right now because all these data-driven methods, actually, the guys on my left-hand side are testing right now also some condition models for robots. But as soon as you test things using synthetic simulated data, you understand that reality is not still well described. So, and this is true in general for robotics. Then as soon as you add aerodynamics and thermodynamics, really, it's a mess. I mean, if you look at the equations governing somehow the mechanics or the aerodynamics and thermodynamics, these are inherently different. So you have ODEs in the for the formers, like ordinary differential equations. So instead, for the latter, you get partial differential equations, boundary conditions, which cannot be solved online. So you have to develop these machine learning methods to model aerodynamics and thermodynamics, and then integrate these models inside each other thing. So I would say that simulations are important, but then you have to get your hands dirty, and you have to understand whether or not simulations are acceptable to represent. Yeah.
So how did the collaboration of this Polytechnic of Milan and Stanford University shape your aerodynamic modeling and neural-based control?
Yeah, I mean, concerning the collaborations with Politecnico di Milano and Stanford, things were really smooth because at the end of the day, we wanted to do two things. We wanted to first get real data for aerodynamics. So we took the robot and we put it on in a wind tunnel. And this is really important to get real data because, I mean, usually aerodynamics of a single body is complex, but is feasible. So if you have an aircraft that moves inside air, more or less, aerodynamics is a complex beast, but it's basically a big single rigid body moving through air. Okay, so, and then you can characterize the turbulence, blah, blah, blah. But then the complexity arises when you have all the cross interferences between bodies, which really increases the level of complexity by a couple of order of magnitude. So we wanted to have the real data because we really didn't know whether or not simulations were reliable. So we put the robot in the wind tunnel of Politecnico of Milan, and then we wanted to build machine learning methods in order to characterize this aerodynamics, and this is what we did with Stanford. The nice thing is that what we try to do with Stanford is physics-informed methods in order to combine physics once again and data. And for the PDEs, the partial differential equations, it's really important because these are very complex beasts to deal with. So you have to really add the regularizers concerning physics.
All right, so what key neural network architect or learning pipeline were used to iterate aerodynamic into the real-world control?
Yeah, concerning this, we're trying to apply modern techniques called the physics-informed methods. Physics-informed methods try to combine both data and physics. So this is cool because, usually machine learning data may suffer from basically a covariance shift. So when you get data out of the distribution, the robot which then inferences actions on top of this out of distribution data might behave as crazy as you want. So the point is, if I don't have data in a certain region, please use physics as a regularizer. And this is basically the idea that we implemented. Okay, these are methods that are called physics-informed methods that we believe to be really important in order to reduce the amount of data that then needs to be used to train machine learning models. But it's also a way in order to have the so-called invariances inside the properties of machine learning methods. For instance, the weight is always positive something. So if you have the weight of something, that this has to be positive. So you would like that these kind of properties are satisfied all over the region of the data.
Okay, so how do you balance between modeling complexity and real-time responsiveness in flight control?
Yeah, this is also a nice question. So in order to balance model complexity and real time, you have to understand, in general, which kind of secondary dynamics has to be taken into account that doesn't mess around. because I mean, adding components of models is not always good, as especially in control theory and in general control actions inference. So usually this is in other fields are called overfitting, like machine learning. But you have to add the complexity that is really necessary and captures the so-called governing dynamics of the system. And then you have to leave all the rest to the robustness of the architecture. And because if you get, I mean, it's better to have simple model but robust architectures rather than complex models which are trained on somehow incoherent data and less robust. So less robustness. So adding a model complexity is not always a good thing if you are not sure that you have enough data in order to train your models. So what we have been trying to do is that we have been trying to add in a sort of Taylor expansion pieces after pieces in order to understand where we were somehow exaggerating, which means that the component of the model that we were adding was too much in order to become somehow to be identified from the data, and then adding it was just giving the robot too much information that instead the robustness of the controller was enough in order to deal with.
Okay, so now what does your momentum-based trajectory planner bring to the mobile flying humanoid? I don't know if I got that pronunciation well.
Multimodal robots are nice because you might have systems that runs, fly, manipulate. So you would like to have a general single approach for multimodal robots. So what we have been trying to do there was to develop trajectory generation systems that could be used for any robots that was equipped with thrusters, and then could also have a degree of mobility when thrusters were off. So, and in order to do so, we have been using these momentum-based controllers and momentum-based representations, because I mean the momentum. This is really technical, but since you went along this way, the momentum of a multi-body system entails most of the, let's say, external dynamics. It's like you have a multimodal system and then you can represent it with a center of mass that moves around, and then the things are moving around it, And then there is this other concept which is the angular momentum. And the angular momentum of a multi-body system is not somehow very interpretable because you don't have a single angular velocity which represents the entire body. So as long as you have a single body, you have the angular velocity. So which means that is the rotational velocity, okay, a single rotational velocity. And then you can represent the motion of this with a trajectory of the center of mass, which is here, and then you have also the rotation. Instead, if you have a multi-body system, then you can still calculate the whole body momentum, but you don't, and you can still calculate the evolution of the center of mass because you have multiple bodies, but you cannot evaluate the rotational total velocity of the rover. So, but you can still do stuff. So the angular, the whole body momentum is a nice quantity that you can use in order to ensure that the robot more or less is going along a direction and is not doing crazy rotations.
So what failure detection or fault tolerant framework guide against turbine failure mid-flight?
Avoidance of explosion. This was the only.
So avoidance of explosion. So
avoidance of explosions was guaranteed 100% by a couple of by a couple of things. So first of all, we added these thresholds on the attitudes of the robot, because what happens once was that the robot took off. Then we don't know why, but it went. Probably we still have that video. The robot went horizontal and then started flying like crazy vertically. And you have an object of 60 kilos that transitions and then starts flying horizontally, and then we had these steel cables that were completely broken in pieces. So we thought, no, probably it's better that we had the latitude control here, so that if the robot inclines too much, then the controller is going to shut down the robot. And then the other fundamental stuff is that there was a guy with a red button on the fuel of the jets, and then basically these were the full tolerance that we had.
Okay. So that was very insightful, and I'm sure the team learned a lot from that failure, right? So how far off is the real world deployment, right? Search, rescue, hazardous inspection, and what trajectory environment must be addressed?
Yeah, so I mean, concerning the distance between our prototypes and the and real deployment, I think that it much depends upon the funding that we are able to find for these specific applications. I think that if we are able to find from 15 to 20 million in 3 years, we can get a platform that can actually be used for search and rescue. In 20 million years.
Okay. So so what team structure and rules, mechanical aerodynamic control here made this possible?
Yeah, I mean, aerodynamics is governed by the Navier-Stokes equations, but these are impossible to be resolved online. So we had to go first through K omega, K epsilon models in order to represent aerodynamics and to have turbulences models. But then we said it's better to go completely data-driven and then add physics to regularize some of the models, and this is what we did.
Okay. All right. Thank you so much, very much for this insightful conversation, right? We are really looking
Thank you.
forward to how far you guys deploy Ion Cube 3, right? And hopefully we keep us updated probably on our next episode podcast. Thank you so much for being here.
Okay, thank you, Joshua. Bye.